Welcome back, everyone, to the final lecture for MAT 2150. Today we will be covering Chapter 5.7 and discussing another application of integration, which is differential equations. Here's our first example of a differential equation. This is an equation that we want to solve not for a variable, but for a function. The unknown here is the function y, which satisfies its derivative is 4x raised to the fifth power. And when we plug into this function 0, the output must be 1. Our goal is to find this function y of x. Now here's our first strategy for solving this type of equation. Let's first write our equation in the Leibniz notation for the derivative. And now let's separate this using our differentials. And we can say that dy is equal to 4x raised to the fifth power dx. And now let's integrate both sides of this equation. That is, the integral of 1 dy on the left-hand side must be equal to the integral of 4x raised to the fifth power on the right-hand side. So on the left, we're integrating with respect to y, so we get y. And on the right, by our power rule for integrals, we get 4x to the sixth power divided by 6, and then our arbitrary constant c. So now we know our function y up to this arbitrary constant. Let's first simplify 4 over 6. We can rewrite as 2 divided by 3, x to the 6 plus c. Now this is what we will call our general solution to the differential equation without including this initial data that y of 0 is equal to 1. Our general solutions are allowed to contain these arbitrary constants. Now let's determine what this constant must be in order to have y of 0 is equal to 1. On one hand, we know that y of 0 is equal to 1, and on the other hand, when we plug in 0, that's 2/3 times 0 to the sixth power plus our constant c. Now this term's gone, this is just 0, and therefore we can say that c must be equal to 1 in order to satisfy the initial condition. Now we can write down our function, or what we'll call our particular solution to our differential equation given the initial data. 2/3 x to the sixth plus 1. Let's try our next example here, where we're given the function, which is a solution to this differential equation, and we're asked to prove that. Our step 1 will be here to compute y prime. Here, y is x times the natural log of x plus x, so y prime, we need to use the product rule and the power rule. Product rule says compute the derivative of the first times the back plus the first times the derivative of the back. And then plus the derivative of x, which gives us 1. Now we can compute the derivative of each piece. Derivative of x is 1, so we get natural log of x plus x times 1 over x and plus 1. Now we can clean it up. We have y prime is the natural log of x plus 1, or y prime is equal to the natural log of x plus 2. Now we have our first derivative, so we can compute the second derivative. That will be step 2. Now we can say that y double prime is equal to 1 over x. Finally, step 3, plug this information back into the differential equation. Y double prime minus 1 over x. This is equal to 1 over x minus 1 over x by our previous work substituting. That's 1 over x minus 1 over x, which is indeed 0. Therefore, this function is indeed a solution. Next, let's find our general solution to this differential equation, and then once we have our solution, check that it is a solution by substitution. Here we have dn dt is equal to 0.23 times n. Our strategy will be the same as before, to separate the variables and then to integrate. So we start with our differential equation. Now everything with an n will go on the left-hand side. Divide both sides by n and then multiply both sides by dt. Now we have the variables separated. So we can integrate on both sides. Integrating on the left-hand side, we get the natural log of n. Integrating on the right-hand side, we get 0.23t plus our arbitrary constant c. Now we want to solve for our solution n. Now we can think of each side of this equation as the exponent to the base e. On the left-hand side, we get n. On the right-hand side, we can simplify. We can say this is point e raised to the 0.23 times t times e to the c. Now remember here that c is an arbitrary constant. And therefore, we can say that so is e raised to the c. So we can relabel and say that we have our solution up to this constant. We're going to say here that e to the c is still just an arbitrary constant c, and say we have c times e raised to the 0.23 times t. Now we have our solution to the differential equation. Let's check that this is actually a solution by computing its derivative. So first we compute dn dt. By the chain rule, that's equal to 0.23 times c times e raised to the 0.23t. But notice here, that is equal to 0.23 times, in parentheses, e raised to the 0.23t, and that is 0.23 times our function n, what we started with. Therefore, the differential equation is indeed satisfied. Next, we have another example where we want to find the particular solution. First, we need to find our general solution in terms of an arbitrary constant. Then we come back and find that arbitrary constant using our initial data. Here first, let's separate the equation. We can say that ds is equal to t cubed plus 9t minus 8 dt. Then we can integrate. On the left-hand side, we integrate 1. On the right-hand side, we integrate t cubed plus 9t minus 8. On the left, we get s. And on the right, we get t raised to the 4th power over 4 plus 9t squared over 2 minus 8t plus our arbitrary constant c. Now, we found our general solution. Let's use our initial data to find the particular solution invoking our initial data. On one hand, we have that s, when we plug in 0, is equal to 83. On the other hand, that will be equal to 0 to the 4th power over 4 plus 9 times 0 squared over 2 minus 8 times 0 plus our arbitrary constant c. Now each of these terms are 0, and therefore we get that our arbitrary constant is equal to 83, and we found our particular solution, t to the 4th over 4 plus 9t squared over 2 minus 8t plus our constant of 83. Next, we have another exponential type of differential equation. Here we're also given an initial data. Let's first separate and find our general solution. We get dB is equal to, or dB divided by b is equal to dt. Now we can integrate. dB over b is equal to the integral of 1 dt. Therefore we get the natural log of b is equal to t plus our arbitrary constant, and then e to the natural log of b is equal to e to the t plus c. Now we play this game with our arbitrary constant. On the left-hand side, we get b. On the right-hand side, we get e to the t times e to the c, where now we're going to say that c was arbitrary, so e to the c is arbitrary. So let's just relabel and say that b is equal to c times e raised to the t power. Now we have our general solution. So let's find our particular solution. On one hand, when we plug in 0, we need to get 100. On the other hand, that's equal to c times e raised to the 0 power, which is equal to c. Therefore, we get that c is equal to 100, and we know that our particular solution is b of t is equal to 100 times e raised to the t power. Next, let's try a slightly more complicated looking example. Here, we first need to separate the variables for this differential equation. So everything with a y will go on the right-hand side, everything with an x on the left. And so we'll get dy divided by y is equal to 7x to the 6th dx. Now we can integrate on both sides. And we get natural log of y is equal to 7 divided by 8 times x, too big, 7 divided by 7x to the 7 plus our arbitrary constant c. 7 over 7 cancels to give us 1. So we have natural log of y is equal to x raised to the 7th power plus c. Now we can solve for y. Take each side of our equation as the exponent to the base e. Here again, we're going to relabel. C was arbitrary, so e to the c is arbitrary. Let's just call that constant c. On the left-hand side, we get y. On the right-hand side, we get e times e raised to the x to the 7th power times e to the c. And now substituting, we get our function y of x is equal to c times e raised to the x to the 7th power. Now we have our general solution to this differential equation. Next, we're going to introduce the idea of a demand function and the elasticity of the demand. The demand relates the quantity of the units purchased versus the price of some object, some product in dollars. And so the elasticity of the demand defined by this function is defined to be the percentage change in the quantity demanded divided by the percentage change in the price. That is, it's the percentage of how the demand changed, how D changed, divided by how the price changed, X. And it turns out we've got a convenient formula, which is the derivative of the demand times X divided by the demand when it's negative. We can see here that the demand elasticity actually defines for us a differential equation. Here we're given the elasticity of the demand. That is, we're given the percentage change in demand divided by the percentage change in price. What we want to find was the original demand function. This is a differential equation which involves the demand function. Let's recall that definition. Using Q is equal to D of X, we can say that our elasticity function is X times Q prime divided by Q, which, when we rewrite it in Leibniz notation, is minus X over Q times dQ dx. So now this gives us a differential equation where Q is the unknown function and X is the variable. Let's write down our differential equation. We have this side is equal to our elasticity function, which is given by X divided by 200 minus X. Now let's separate the variables. We need everything with a Q on one side and everything with an X on the other. So we can leave dQ and Q on the left-hand side. On the right-hand side, let's get rid of this negative. Let's divide both sides by negative X. So we'll get 1 over, now I'm making this side negative, that's X minus 200. Now let's integrate on both sides. Integral of dq over q on the left is equal to the integral of 1 over x minus 200 on the left. On the left, we get the natural log of q. On the right, we get the natural log of x minus 200 plus our arbitrary constant c. So now let's solve for C, or let's solve for Q, and then we can solve for our arbitrary constant C. That is, Q is equal to, what operation are we doing? E raised to the natural log of Q is equal to E raised to the natural log of X minus 200 plus C. Now this is entirely in the exponent. Let's put some parentheses around it so we see that. On the left-hand side, we get Q. On the right-hand side, we get, let's see, this is E raised to the natural log of X minus 200 times E to the C. Let's do our relabeling. E to the C goes to C. So we get Q is equal to C times X minus 200. Now we can solve for C. We know Q is equal to 150 when X is equal to 5. So using our initial data, we get 150 is equal to C times 5 minus 200. Therefore, 150 is equal to C times negative 195, and C is equal to 150 divided by negative 195. Which we can simplify. 150 divided by 5 is 30. So 195 over 35, that's plus 9 more, must be 39. Now we know our solution. We found our demand function. We can say that d of x, or q, which is equal to d of x, is given by negative 30 over 39 times x minus 200. Next, let's try a slightly more complicated looking example and apply our idea of separation of variables. First, we'll rewrite our differential equation using Leibniz notation. Now our goal is to get everything with an x on one side and everything with a y on the other. The trick here is to rewrite the differential equation. Let's factor out the common term of x. Now we can divide both sides by 1 plus y, and that will be equal to x dx. Now we can integrate both sides. On the left-hand side, we get the natural log of 1 plus y. On the right-hand side, we get x squared over 2 plus our arbitrary constant. On the left-hand side now, we'll get e raised to that stuff is equal to e raised to this stuff. So 1 plus y must be equal to e raised to the x squared plus 2 times e to the c. We play this game of relabeling with our arbitrary constant. And now we can say y is equal to c times e raised to the x squared over 2 minus 1. Now we can use our initial data. When we plug in 0, we're supposed to get 1. On one hand, we have y of 0 is equal to 1, and on the other, it's equal to c times e raised to the 0 squared over 2 minus 1. Well, that's equal to c times 1 minus 1. and therefore we can say C must be equal to 2. Now we have our solution, y of x is equal to 2 times e raised to the x squared over 2 minus 1. One more example of separation of variables. Here, our first step is to rewrite the equation in Leibniz notation. Also, let's get rid of this negative exponent. Now we can separate. We get y cubed dy is equal to 5 dx. Now we can integrate. And so we get y to the fourth divided by 4 is equal to 5x plus our arbitrary constant c. Now at this step, let's go ahead and find c. What we know is that when we plug in 1 for x, we get 1 out for y, or that y of 1 is equal to 1. Let's use this initial data to find c. Y of 1 raised to the fourth power over 4 must be equal to 5 times 1 plus our constant c. That is 1 over 4. 1 to the fourth over 4 is equal to 5 plus c, or 1/4 is equal to 5 plus c. So c is equal to 1/4 minus 5, which is 1/4 minus 20 over 4, or negative 19 over 4. Now we know our solution, although we haven't solved for y yet. We can say that y raised to the fourth power over 4 is equal to 5x minus 19 over 4. Now let's multiply both sides by 4. We get y to the fourth is equal to 20x minus 19. Now let's compute the fourth root on both sides. And we can say that y of x, we need to think about this, is plus or minus the square root, the fourth root of 20x minus 19. And now let's pose the question, positive or negative? When we take the fourth root, we get this positive or negative case just from the algebraic operation of taking the fourth root. But think about it, which case should it be? Should it be positive, or could it be negative, or could it be both? What we do know is that we must satisfy the initial data. When we plug in 1, we have to get 1. Y of 1 here, is it going to be positive or negative, question mark, will be 20 times 1 minus 19, which gives us positive or negative the square root of 20 minus 19, or 1. This is plus or minus 1. Now this has to be positive. Therefore, we can eliminate the negative case. We know it must be the positive case in order to satisfy the initial data. So now we can write down our solution. Our particular solution to this differential equation is the fourth root of 20x minus 19. Now we have an example with continuous compound interest. We're first going to write down the differential equation which models the amount of money in someone's account after T years. And let's think about it. The more money you have in the account, the more interest you can earn. Or the change in the money in your account is proportional to the amount of money in the account. So we can quickly write down that differential equation using that idea. The change or increase in money in the account is proportional to the amount in the account. That is, the more money you have in the account, the more interest you earn. So let's write that down as our differential equation, keeping in mind that we know our interest rate. How is the amount of money in the account going to change? dA dt, the derivative, tells us how the amount changes. It's going to change by the interest rate, 0.385, multiplied by the amount of money in the account at time t. So now here is our differential equation. This says the change is proportional to the interest rate times the amount of money in the account. Now we can solve our differential equation. dA dt is equal to 0.0385 times A. Let's separate to get dA over A is equal to 0.0385 t dt. Then we integrate on both sides to get the natural log of A is equal to 0.0385 t plus our arbitrary constant. Now take each side as the exponent to the base e. We get A is equal to some arbitrary constant c times e raised to the 0.0385 times t. Here we have our general solution. What we now need to find is our particular solution, taking into account that we have a starting amount of $900. So we can say that at time equals to 0, the starting time, we need to have $900. On the other hand, that's equal to c times e raised to the 0.0385 times 0, which simplifies to c times e to the 0, or just c. And therefore, our arbitrary constant is equal to 900. Now we can write down our particular solution to this differential equation. We can say A of t is equal to 900 times e raised to the 0.0385 times t. Now that we have our solution, we can actually answer a question regarding it, how much money it will be in the account after a certain amount of time, and what will be the rate of change of money in the account at that time. So here is our solution. We can quickly compute A of 6 as 900 times e raised to the 0.0385 times 6. Let's see, 900 e raised to the 0.0385 times 6. After 6 years, I got we should have, let's see, there we go, $1,100.87. So now this is the amount in the account after 6 years. Let's next compute a prime of 6. A prime of t is equal to 0.0385 times 900 e raised to the 0.0385 times t by the chain rule. And therefore, a prime of 6 be this quantity when we plug in t is equal to 6. And you can see that'll be the same as this value, just multiplied by 0.0385. And here I got $43.65. This quantity tells us how A, the amount in the account, is changing or increasing at the instant where at t is equal to 6 years. Now lastly, let's decide what does a prime of 6 divided by a of 6 actually represent. Let's first recall our differential equation. dA dt is equal to our interest rate 0.0385 times a. So what in the world will this quantity actually give us? Let's rewrite it in terms of Leibniz notation. This is dA dt, when we evaluate it at t is equal to 6, divided by a, when we evaluate that at 6. But observe here, on the other hand, what happens when we just take our differential equation here and divide both sides by a? That is dA dt divided by a is equal to our interest rate. So this quantity, regardless of where we evaluated it at, it matches with our differential equation. This must give us the interest rate. So our answer to this question is 0.0385, and this quotient gives us the interest rate. We can tell that just by studying the original differential equation that we started with. This ends our last lecture for MAT 2150. I hope you all have a great semester and good luck with your final exams.